I would like to talk about some rigidity result of complete minimal submanifold in hyperbolic space. I'll talk about topological structure of minimal submanifolds. In particular, I would like to study some Bernstein type theorem, and secondly, I'll deal with non-existence of L2 harmony 1 forms on minimal submanifolds in hyperbolic space, and I'll give you some first eigenvalue estimates results and some examples of minimal submanifolds in hyperbolic space. Okay, before we study complete minimal submanifolds in hyperbolic space, let me show you some well-known facts in Euclidean space. First of all, M is said to be minimal in Riemannian manifolds if the mean curvature H vanishes, and we'll denote by A squared the length of the second fundamental form A. One of the interesting question is due to Bernstein, which says that is an entire minimal graph over Rn hyperplane. This is Bernstein problem. This problem is completely solved. If dimension is less than or equal to 7, then it's okay. However, the dimension is bigger than or equal to 8, then there is some there exists minimal cone, which is not a hyperplane, constructed by Bombetti, George, Giusti. So we want to generalize this problem in the following direction. We note that the minimal graph is stable. So here, by stability, I mean that if the second variation of its volume is always non-negative for any normal variation with compact support. In particular, when the codimension is equal to 1, minimal submanifold M is stable if and only if this second variation of its volume is always non-negative. So we can change the question as follows. Is a complete stable minimal hypersurface M in Euclidean space hyperplane for n less than or equal to 7? As I said before, if n is bigger than or equal to 8, then there exists some example of minimal graph, which is not a hyperplane. This question is still open, but we have some following partial results. This question is true if for complete stable minimal surface. It was proved by Dogarmo and Penn, Fisher, Colbury, and Shen. And for any dimension n, we have affirmative answer under some additional condition here. If L2 norm of second fundamental form A is finite, then it's still true. Moreover, if ln norm of the second fundamental form is finite, then it's still true. Here, the quantity Ln norm of second fundamental form A is called total scalar curvature. So let me show you some results on topological structure. If M is a stable minimum hypersurface in a Euclidean space, then M has only one end. And if we have sufficiently small Ln norm of second fundamental form, then M should have only one end. Here we don't assume the stability of minimal submanifold M. And here CS means is a sublab constant. It turns out that the upper bound C1 here in this theorem can be improved. Okay. From now, denote by Hn the n-dimensional hyperbolic space of constant sectional curvature minus 1. Then we have some analog of previous theorem. Let M be an n-dimensional complete immersed minimal submanifold in hyperbolic space where n is bigger than or equal to 5. And we suppose that Ln norm of second fundamental form A is sufficiently small. Then M should have only one end. Okay. Let me give you some idea of the proof. The first step is to suppose that M has at least two ends. So we will prove by contradiction here. Then if M has more than one end, then there exists a non-trivial bounded harmonic function U on M, which has finite Dirichlet energy. The second step is to use Wagner formula for harmonic function U. The formula is like this. And third step is to apply the Ricci curvature estimate, which was done by Long. The Ricci curvature estimate is the following. Let M be an n-dimensional complete immersed minimal submanifold in hyperbolic space, then Ricci curvature of M is less than or equal to minus n minus 1 minus n minus 1 over n times A squared. So if we put f to the absolute norm of absolute value of gradient of U, then it follows from the previous result we have this inequality here. Here U is on the harmonic function as before. Yeah. The first step is to multiply a nice test function phi and integrate over M. It's just a computation. Yeah. Next step is to apply sublab inequality due to Hoffman and Sprague. And we will use the first eigenvalue estimate for complete minimal submanifold in hyperbolic space, as I told you. Then we have after some long computation, we have this inequality here. We have two constants A and B. here A and B came from Schwarz inequality. Okay. Here A is a constant, so we can choose any positive number A for our purpose. So okay, here we have, if we choose A and B small enough, then this is some positive number, and here phi is a nice test function which satisfies some fixed point, let's say P, but we will use distance function, so I'll use origin. So here phi satisfies this. Here phi have value like this. Here gradient of phi is less than or equal to 1 over r. So we can control this term because f was the absolute value of gradient of u. So this, if we choose r large enough, then this term less than or equal to less than or equal to this term, bounded by this term, and f was the length of gradient of u. So here u is a harmonic function with finite Dirichlet energy, so we can control this term. Okay, so this term is some number, and this term goes to 0 as r goes to infinity, and this term is some positive number if we choose A and B small enough. And then we should have this term vanishes. So, which means that f is constantly 0. It means that u is a constant. But this is contradiction because we assume that u is a non-trivial harmonic function. Yeah. This contradiction follows from the assumption that m has more than one end. So therefore we can obtain conclusion. In the previous proof, if we do not use the first eigenvalue estimate, this inequality, then we have some similar result here. I mean that in the previous proof, here we used the lower bound of eigenvalue, but if you do not use this lower bound, instead of using this lower bound, but we calculate directly, then here lambda 1 and if we use this inequality here, then we obtain the following result. This theorem says that the first eigenvalue is a little bit related with the topological structure of M. Okay, let me give you some results on non-existence of electroharmonic one-forms on minimal submanifolds. Okay, omega be an electroharmonic one-form on M, which means that Laplacian of omega is 0 and the electronorm is finite. There are some results in Euclidean space. First thing is, if M is a complete stable minimal hypersurface in Euclidean space, then there are no non-trivial electroharmonic one-forms on M, which was done by Miyaoka. And second thing is, due to Professor Yoon is here, he proved that if M is a complete stable, complete minimal hypersurface with sufficiently small Ln norm of the second fundamental form, then there are no non-trivial electroharmonic one-forms on M. It turned out that his result is still true for arbitrary codimension, and the upper bound of C2 here can be improved. Okay, let me show you some analog results of hyperbolic space. Let M be an n-dimensional complete immersed minimal submanifold in hyperbolic space where n is bigger than or equal to 5. Then, and suppose Ln norm of second fundamental form is sufficiently small. Here C sub S is still sublab constant. Then there are no non-trivial electroharmonic one-forms on M. As before, if we do not use the first eigenvalue estimate, then we obtain the similar result. Okay. To manage the higher codimension case, we need some computation. First one is due to Sprague. He proved that for an n-dimensional minimal submanifold in Euclidean space, variational vector field E given by phi times nu, the second variation of its volume satisfies this inequality. This is different from the codimension 1 case. If we think one-dimensional case, then we have this equality here, but no more true for higher dimensional case, higher codimensional case. A similar computation shows that for an n-dimensional minimal submanifold in hyperbolic space, then we have similar second variation inequality here. We have still inequality here. Okay. Motivated by the above inequality, we will call minimal submanifold in hyperbolic space superstable if for any function phi lying in W012 of M satisfies this inequality. This definition is exactly same as the usual definition of stability when and codimension is 1. Wang introduced the concept of superstability to prove that if M is a complete superstable minimal submanifold with finite total scalar curvature in Euclidean space, then M is an affine and plane, which means totally geodesic one. Okay, we want to generalize. The above results in hyperbolic space. Okay, let M be a complete superstable minimal submanifold in hyperbolic space, and suppose that first eigenvalue of M is greater than 2n minus 1 times n minus 1. Then there are no non-trivial L2 harmonic 1 forms. This is a little bit strong assumption here. By definition, we can obtain this corollary here. That you prove that there exists a non-trivial L2 harmonic 1 form on M if there exists a codimension 1 cycle which does not separate M. I'll draw a picture topologically. This is M. Here we have two genus and we have several and here. Then here we can find such a codimension 1 cycle which does not separate M like this. Yeah. This codimension 1 cycle does not separate the surface of M. Yeah. Okay.
If you have more than one end, do you always have one of these harmonic 1 forms? Harmonic 1 forms? If you have more than one end?
More than one end?
Do you always have non-trivial L2 harmonic 1 forms?
I'm not sure, but this is one possible condition here. Yeah. It's a very interesting question. Yeah. Okay, so if we have the previous result, then we have corollary like this. Let M be a complete minimal submanifold in hyperbolic space satisfying this first eigenvalue estimate. Then there exists, suppose there exists a codimension 1 cycle in M which does not separate M. Then M cannot be superstable. Why this is true? It's simple because from the Dajcik's result, this assumption gives us that there exists a L2 harmonic, non-trivial L2 harmonic 1 form. But in the previous result, if M was superstable, then there is no non-trivial harmonic 1 forms. So we have this corollary. Another remark is that let f be a harmonic function on M with finite Dirichlet energy, which satisfies these. Then its differential df is L2 harmonic one form on M. Therefore, we have another corollary here. If M is a superstable minimal submanifold in hyperbolic space and first eigenvalue is bigger than or equal to this number, bigger than this number, then there are no non-trivial harmonic functions on M with finite Dirichlet energy. Okay. Let me give you first eigenvalue estimates for complete minimal submanifolds in hyperbolic space. First nice result in this direction is due to Chung and Leung. And they proved that for an n-dimensional complete minimal submanifold M in hyperbolic space, then the first eigenvalue is greater than or equal to m-1 squared divided by 4. This is, they gave the lower bound of the first eigenvalue. Here, we mean the first eigenvalue means for Laplacian operator on manifold M. This inequality is sharp because when M is totally geodesic, then we have equality here. So this is sharp inequality. Another interesting result is due to Kendall. He proved that if sigma is a complete, simply connected stable minimal hypersurface in the three-dimensional hyperbolic space, then lambda 1 has upper bound and lower bound like this. Okay, I would like to generalize this theorem in two directions. In one direction, one possible way is to generalize ambient space. Another possible generalization is into higher dimensional case. So I'll give you some partial result. This one is the generalized ambient space. Let sigma be a simply connected stable minimal hypersurface in a three-dimensional simply connected Riemannian manifold M3 with sectional curvature satisfying this upper and lower bound. Then first eigenvalue has lower bound as a squared divided by 4 and upper bound 4 times b squared divided by 3. Another generalization is like this. If we have L2 norm of second fundamental form is finite and we assume stability, then the first eigenvalue is given by this inequality here. Instead of assuming simply connectedness of minimal surface, we assume that the L2 norm is finite. Okay. Let me give you some idea of this theorem, the proof of this theorem. We have to prove two inequality here. So first we prove this inequality. it is upper bound. First step is to use the existence of global polar coordinate from the Gauss curvature equation. Intrinsic Gauss curvature equation is given by this Gauss curvature equation. Here we use the ambient curvature assumption. So this term is always negative. So since the Gauss curvature is negative and sigma is simply connected, therefore we have some global polar coordinate. This polar coordinate is it was used by various people. And second step is to use stability inequality. Here, this is the stability inequality, and this we write this rich bar, and finally we use the sectional curvature of ambient space. So we have this inequality here. And third step is to choose a nice function, which is a radial function, satisfy f0 is 0 and fr is to be 0 for some given number r, bigger than given number r. And for convenience, we assume that f is piecewise linear in R. Therefore, f double prime is 0, except for finitely many values of R. So here, f is like this. We have some given number R, then piecewise linear function here. This is f. Next step is to use Gaussian curvature explicitly like this. So we use this inequality here. Actually, we replace k sigma with this term here. Then we can rewrite inequality like this. Okay. The next step is to use to integrate integration by part twice and use some property of our nice function f. Let me give some explanation of this equality. Okay, we have this term here. Then we apply the integration by parts twice now. First, scalar b r minus here we used integration by part once. Here f vanishes at r and 0. So this term vanishes, and we applied integration by part again here. Then can you see this? Okay. This term vanishes as well because our f is satisfies 0 at the end points. So and here if we differentiate r f squared with respect to r twice, then here we have some nice property of f, because f is piecewise linear, so this term vanishes. So we have equality here as this computation. Okay. Next step is to use the previous results. So therefore, we obtain this inequality here. Hence, it follows that the first eigenvalue is less than or equal to 4 times b squared divided by 3. So we proved upper bound part. And next, we will prove the lower bound part. This is much easier than the upper bound part. First step is to use the Laplacian of distance function r with some comparison theorem of distance function. Then we have this inequality here. And second step is to integrate both sides over omega, any domain omega. Then we have this inequality here. Here, in this equality, we use the Stokes theorem. Yeah. And now we apply Chigurh's inequality. Chigurh's inequality is like this. Lambda 1 is greater than or equal to Chigurh constant squared divided by 4. Here, Chigurh constant is given by this, like this. Integral of for any subdomain of omega of sigma, the Chigurh constant is defined by this. So in the second step, we have the lower bound of Chigurh constant. So we obtain the first eigenvalue estimate here. Next, let me give you some idea of proof of this theorem. By Chung and Lung's result, it suffices to show that lambda 1 is less than or equal to n squared. Okay, first step is to use the Rayleigh quotient here. For here, BR is a ball of radius r centered at P. Here, P is any given point P. And function phi is any compactly supported Lipschitz function. And in this inequality, we substitute A times F for phi in the above inequality here. And third step is analyze the second fundamental form A. We will use the Chern-Tokarev-Kobayashi inequality here. And multiply both sides by function f squared with compact support in BR and integrate over B sub R. And now we shall use stability inequality here. Substitute A times F for F. So here we substitute. Okay, after some computations and using Schwarzschild inequality, we have this inequality here. Here alpha is the constant from Schwarzschild inequality. Okay. Our assumption was, our conclusion was lambda 1 is less than or equal to n squared. Now we suppose that lambda 1 is bigger than n squared. Then choosing alpha sufficiently large and letting r goes to infinity, then we get the conclusion here. Because this term is some given number and this term goes to 0 as before, because f is some nice test function. And therefore, this term goes to 0. And this term is some positive number because we assume that first eigenvalue is bigger than n squared. And this term is some positive number controlled by these terms. Therefore, if we let r goes to infinity, then this term should vanish, which means that the length of A, second fundamental form A, is constant. However, we know that since L2 norm is finite and the volume of M is infinite, it follows that A is constantly 0. If not, then we have some contradiction here, which means M is a totally geodesic hyperplane. We know that the first eigenvalue of totally geodesic 1 is equal to n minus 1 squared divided by 4. This is due to Mackin's result. So this is contradiction because we suppose lambda 1 is bigger than n squared. So this is contradiction. Therefore, we get the conclusion here. Okay, I'll give you some examples. First one is a spherical catenoid in hyperbolic space. Tokarev-Deja gave a parametrization of spherical catenoid in H3 like this. Okay, using this useful lemma, we can obtain some interesting result. This lemma says that let M be a completely stable minimal hypersurface in hyperbolic space with finite L2 norm of second fundamental form A, then the L2 norm of gradient of A is finite. Using this lemma, we can show that the spherical catenoid M alpha MA in hyperbolic three-dimensional hyperbolic space is unstable for this A. Here we have some one parameter family of spherical catenoid. Here A is bigger than 1/2. Okay. Note that this unstable catenoid has index 1. Actually, any unstable catenoid has at most index 1. So the proof of this corollary is like this. First step is to show that this spherical catenoid has finite L2 norm of second fundamental form A. This is because the first fundamental form is given by this term, and second fundamental form A is given by this, and the volume form can be written as this term. Then L2 norm of second fundamental form is integration of this term with respect to the metric here. Then this integration is finite. So we have finite L2 norm of second fundamental form for this spherical catenoid. Second step is to define some function f, which is given by 4 times integration of a squared minus m integration of gradient a squared. This is why we define this function, because in the above lemma we showed that this inequality. So for 2-dimensional case, we put n is equal to 2. Then we note that if m is stable for some number a, then this function is non-negative by the above lemma. Sorry. Using this inequality, this equation, and we have some equality here, and by using computer we can show that f of a is negative for some number a, which is less than 0.73. Therefore, we get the conclusion. I mean that spherical catenoid is unstable for some a. Another interesting example is hyperbolic catenoid in hyperbolic space. Generating curve is like this, x, y, z in the hyperbolic plane H2. H2 is here. So lying in 3-dimensional Lorentzian space. So first condition is hyperbolic plane, and second condition means this generating curve is parameterized by arc length. And hyperbolic catenoid is defined by like this. And using this equality, we can determine y and z in terms of phi. Here phi is an integration of x in terms of x. Okay. Here is some theorem. Let MT be a family of hyperbolic catenoid in hyperbolic space defined as before. Then MT is a complete stable hypersurface in hyperbolic space for some for some t. Therefore, we have one parameter family of hyperbolic catenoid which is stable. And moreover, it is not hard to see that this hyperbolic catenoid satisfy that L2 norm is finite. So my condition as before was have some meaning in some sense. Okay, another example is helicoid in H3. Helicoid is defined by this. Here, alpha is called angular pitch. Some computation shows that first fundamental form is given by this, and second fundamental form is given by this. So, since this denominator is less than greater than or equal to 1, therefore a squared is bounded by some number. Using this inequality, I can show that some result. Helicoid, one parameter family of helicoid with angular pitch alpha squared less than or equal to 9/8 is stable. So we have some stable helicoid in three-dimensional hyperbolic space. Yeah. Thank you for your attention.